Okay, let's start. Okay, first let's review last class. Okay, so last class, okay, we finished the basic feature for the TCP. Okay, like for the TCP part, we discussed TCP, the header, so including the source and destination port number and sequence number, ASIC number, and also other parameters like the RWMD, that field value for the flow control, and like the SYN or FIN for the three-way handshaking or closed start connection, and also checksum. And for the TCP, also we discussed how to set window timeout interval, and we also validate the TCP reliable data transfer. Okay, after this, we continue to discuss about the TCP flow control. It will not overwhelm the receiver buffer by transmitting more data and too fast data to the network. And so this one is easy to adjust. We just there is the specific window, right? So the called RWMD. We just the receiver let sender know what's the available number of the bits in the receiver's buffer, translate. So and then that need to control the sending rate need to smaller or equal this value. Okay. And after this, we also discussed the TCP, three-way handshaking, and how to close that connections. Okay, for that we can see, like from the client to the server, they need to use SYN, that bit 1, and also start one single number, for example X, and then server gets this information. No, this client called the connect. Then that use accept method to create connection socket to give that the feedback, that is ACK the bit 1, also give feedback ACK number that equal X plus 1. And at the same time, the server also need to know to make sure that the client also will be ready to response message. So also generate new SYN bit equal 1, and also the new signal number equal Y. Okay, to check out the client feedback. The client also give feedback or ACK equal 1 or ACK number equal Y plus 1. That means both sides. After this, both sides are ready to transmit data over this connection. And if we close that, also we use FIN, the bit 1, and generate signal number. Same thing like the setting up that part. Okay, after this basic feature, we discussed, what's the cost and reason for the conjunction. Okay, we discussed 3 scenarios. And the first one is we just consider for the simple case, and there are just one router with the limited buffer size, and there are no retransmission. And for this case, if there are 2 connections, over the link, and each one just share our 2. So if we increase the sending rate lambda in, so lambda out also will increase. After lambda in is larger or equal R over 2. So the output throughput equal lambda out equal equals R over 2. Okay, then we consider the second case. Okay, for this case, limited buffer size, we need to address like the first thing is packet loss. For the packet loss, it will reduce the maximal that is the output throughput. And because that need consider the retransmission. And the second case is that because of the small timeout interval, and which lead to the also some unneeded retransmission also, which it also reduce that the maximal output value. Third case, if we assume there are multiple sender, multiple hops, for this case, and we can see that curve in the beginning, if we increase the data rate, also output will also increase. After one threshold, so that output throughput will decrease. This is interesting. So because multiple connections share that the link. So for this case, and we need to consider sometimes based on the network congestion level, sometimes we need to increase that the Windows data rate if that network is good, and bandwidth is larger. And sometimes we need to decrease that if network is the congested. And for these three things, okay, we give some insight of these three scenario. And after this one, we go to our contract control problem. Okay, for contract control idea is that we know there is the CWNT, this is Windows size. We need to there are two types of contract control. One is end-to-end, like discussed earlier. And that means sender just based on observed feedback, like the ACK or like the time order value to make decision. Need to linear increase that or need to cut window size in half. So contract control regarding the sending rate, and like the sender's window size, because that window size determine that sending rate. And so first we discussed AIMD. So this is regarding the conjunction avoidance stage. So linear increase, it finds that packet loss that cut window size in half. Linear increase and cut window size in half. After this, we need to discuss, we will not, so there are three stages, for that case. And the first stage is like this slow start. Last class, we stop here. And slow start is that in the beginning, we said that window size is small, just one MSS. So then if get feedback 1 over 1 RTT, we need to double the window size. 2, 4, 8, 16. And if we continue doubling that window size, which lead to maybe the faster congestion for the network. So after one threshold, we need to consider from the slow start into the contract avoidance. Like we can say if the window size is larger or equal to the threshold, for this case, next state, that is the, let's see. That is the congestion avoidance. For the congestion avoidance, that means, we can say we need to control that the increase rate. We from the double that transfer to the linear increase that. If get ACK, we just, one time we add one, value for the window size. Another case is that for this stage, also we need to check out if there are some duplicate packet. If there are 3 duplicate packet, we know that is we need to do the faster retransmission. So that into the new state called fast recovery. FR. And for this state is if get an not a duplicate ACK, get new ACK that also into the contract avoidance. From the contract avoidance to the slow start, if that node, the timer expired, reach to the time order value, that need to go back to the slow start. So set one is set 1, another one said, we need to say the very important thing is that how to update the window size, the threshold, this SS threshold. Threshold equal that last window size over 2. And for the slow start parties, we need to set that, window is equal 1. And if we into the fast recovery, this stage, we need to set, window set a first update threshold, equal to window over 2, and use that threshold plus 3. Then, for this case, for the retransmit missing segment. And from the fast recurring to the slow start, similar things, if the timeout, reach the timeout value, and we also need to update the threshold. Anytime for the packet loss, we need to update the threshold, just half of window size. And go to start, transfer to slow start, we need to set window size 1. This is that basic feature for this 3 stage. This is the classical TCP contract control for the internet. Current internet use that. And this is important, if you understand contract control, you know this 3 stage. And this stage, contract avoidance, we call this is the stable stage, like AIMD. We in this one, if we get that linear increase and get 3 duplicate ACK and go to that the fast recovery and then get a new ACK, we need to go back to linear increases. In order to understand that, and if we get a new ACK for this stage of slow start, we need to double window. And for this stage, we linear increase that. And for this one, go back conjecture avoidance, that means linear increases. Okay, here is the one, I think, interesting questions. Let's review, okay, the last concept for the three stage. And there are three questions. Okay, let's together to do this. First question, there are three stages. First one is slow start. We, okay, write as SS. Second one is, okay, conjecture avoidance. We consider CA, okay, conjecture avoidance. The third one is the fast recovery. Okay, we consider FR. Okay, so the first question, based on that figure, this figure, you need to consider for these points belong to which stage. Okay, based on that feature. Okay, you need to consider, okay, for this time unit, for this node, belong to which stage? Okay, the first question. Okay, which state for this in these curve nodes? Second state is that you need to update this threshold. Okay, as threshold. Okay, threshold. Okay, so we know, okay, if there are packet loss, we need to consider update that. So that is equal threshold equal the last window size over 2. That is equation is this. Third one question. Okay, you need to consider, okay, for the packet loss, okay, so you need to determine what's the reason for this packet loss. Okay, there's two reasons. One is 3 duplicate ACK. Okay, 3 duplicate ACK. Second one is the time order value. Okay, so for these three questions, we can say the first one I can summarize again. First one is consider from this curve. Okay, from this this curve. So you need to know determine which time points or which node belong to which stage, three stage. Second one is that update the threshold. Beginning is 8. Okay. Third one is that for the time point, for the time out that value, you need to determine that node belong to which reason. Okay, the 3 duplicate ACK or the time out value. So if we want to consider 3 duplicate ACK, that need to check previous the figures. We know for 3 duplicate ACK, that means we need to update. First one, we update threshold, and that value equals threshold plus 3. And so if we consider that value is the time out value, so that means if next point that equal 1, we say that window is 1. So that time the packet loss because of the time out value. Okay, this window size is easy. And for this one, you need to consider for the slow start is double. Okay, so exponential increase. That state nodes belong to the slow start. And conjecture avoidance, that is linear increase. Okay, this one is just for the because of the 3 duplicate ACK next point is fast recovery. Okay, to jump that. Okay, if we know these three questions, then one by one to consider for each node how to first one like to address first question. Okay, first question is that for all these nodes we need to mark that belong to which stage. Okay, first one definitely this is slow start. Okay, this node. And the interesting is that if that is the next node, if that continues the slow start, so that need to become 2 because that is 1, 2, 4, 8, 16. But the next one is also 1. So this is interesting. If that one, the reason just 1, okay, so packet lost for this point. Okay, there is packet loss for this point. And if that packet loss, okay, we need to consider, okay, so this packet loss because of 3 duplicate ACK or that is time out value. If that 3 duplicate ACK, that first need to update the threshold. Okay, that equal of this 1 over 2, that is 0.5. Okay, then the next value need to equal the 0.5 plus 3. Definitely this is not, okay, we exclude this, okay, this option. This is not a 3 duplicate ACK. There are just one case is time out value. Okay, if the time out value, we set that 1. So this is one node, okay, for the packet loss. And the reason for this node is time out. We need to mark this is time out. Okay, and then this node also is slow start. Okay, this is the SS. Okay, SS. Okay, and So this is a feature. And if that is timeout value, also we need to update the threshold. This is the 0.5 because 1/2. Okay, for the first two, we mark this. And then, then because threshold is 0.1, and the next point definitely is larger than this one. That into the conjecture avoidance stage. Okay, if larger than this, so next stage. So this from this node, okay, to the here, we call this is linear increase. Definitely, this is the CA conjecture avoidance. Okay, get ACK. Okay, we linear increase. Okay, that is the 2, 3, 4, 5, 6 linear. And then there is okay for this there is packet loss because that next window size okay decreased. Okay, so we first need to check out this node. What's the reason for the packet loss? And we check that this is not 1. Definitely this 3 duplicate ACK, 3D. Okay, for the packet loss, first update the threshold. This is, we can say this is 10, 11, 12, 13, 14. So that is threshold is 14/2. Okay, this is 7. So we need to consider threshold like here. Okay, 7. Okay, if that's 7, okay, then this node, this interesting node, because if get 3 to ACK, so that into the fast recovery stage. So this one is fast recovery stage. Okay, threshold is 7. And the next one, if check next, get a new ACK, okay, and that into the, okay, special, get a new ACK that into the conjecture avoidance because that linear increase. So this is also a CA conjecture avoidance stage. Okay. And the next is that, okay, we since we were observe that window size will decrease into the 1. Okay, that is one the reason just timeout value. Okay, this point, okay, there is event called timeout. Okay, and if that timeout, okay, first thing we need to update threshold. Okay, this is, we can say that is the 15, 16, 17, 18, 19. Okay, 19/2. Okay, that is, okay, 9.5. Okay, 9.5, like from here, that into this one. Okay, and for the 9.5, then, okay, because that timeout equal, that because of timeout, we set window size 1. So this, from here, that into the slow start. Okay, because 1, 2, we can say 1, 2, okay, 4, okay, next one, that is the, still is the, 8, 16. Okay, we double that, right? Okay, so because this window also that's smaller than that, right? And here for this point still, okay, this is slow start stage. Okay, so interesting is that this here is from this one there is one okay timeout because next one is the okay the window size 1. So this is also packet loss. We need to determine this is also timeout value for this reason, timeout value. And update, this is the 16. So 16/2 is 8. So next thing we need to update from this one to become 8. Okay, if that 8 also this into, okay, the slow start. Okay, so from the 1, okay, 2, 4, 8. This is, we can mark this is slow start. Okay, and after, if larger or equal the threshold, okay, the next one into the conjecture avoidance. Okay, so we finish this figure. So based on that curve, this curve, we can infer that these nodes belong to which stage. And for there are 3 nodes, this first one, second one, and third one. Okay, this, okay, because of the packet loss, we need to know which reason for the packet loss. That is, this is 3 to ACK because next window is not 1. And this 2, okay, because of the timeout value, reason in next one is 1. So easy to determine this is 3 duplicate ACK or timeout value. And then we need to consider how to update the threshold. Okay, that just equal the last node if that packet loss. This window value over 2, okay, over this over 2, this over 2. Okay, and how to consider this is in this 3 stage. We just to determine, okay, this linear increase is double that. So this if the exponential increase that is so start linear and contract avoidance, and fast recurring just one case. If that's 3-tuplet ACK, next node is fast recurring. Okay, so this is we use this figure, okay, to validate the last algorithm for the classical TCP contract control, okay, to address these 3 things, okay, different stage, threshold, and the reason for the packet loss. Any questions for this figure? Okay, so for the midterm exam, there are no question regarding this figure, but for the final exam, there is long answer questions, okay, for this figure. Okay, I give the same figure, okay, you need to address the same 3 questions. Okay, first one, consider which node belong to which state. Second one, update threshold. Third one, consider the reason for these 3 nodes. Okay, I just changed the curve. For example, this is maybe nonlinear increase and then linear increase. Okay, just change the curve, but the same questions for the final exam. Here is we can discuss these examples, and maybe in the future you can review this discussion. Any question? No question. Let's continue to discuss next part. Any question? Okay, no question. Okay. Previously we discussed the TCP classical contract control, and so that's a good one. So there are 3 stages, and special in the stable stage like contract avoidance, that a linear increase cut window size in half because of 3-tuplet ACK. And so for that case, like for the AMD one, and a linear increase cut window size in half, linear increase cut window size in half. We consider max window size is W max. And then if we cut window size in half, that is the W max over 2. And for this case, for the transmission data, like the area under this curve, this under area like under this curve. Okay, so for this case, for area under this curve, and so that regarding that throughput, transmit data. So is there the better way, than this AMD to fully use that usable, the bandwidth? That means can we improve the throughput? Okay, that means how to increase that area under the curve. Okay, so the solution is there is another port called TCP cubic. Okay, the idea is can we design that window update with the nonlinear curve like this? Okay, this. If we do the nonlinear curve, so we can see we can increase additional area, right? So what's the motivation? We use the nonlinear curve. Okay, so that part is that. So in the beginning, in the half part, that current case is naturally not congest. So we consider the faster to increase that window. So the slope here is larger. And if that window approach W max, the contraction level, contraction, so we can decrease, we can say slowly increase that window. So that means in the beginning part, the delta W is larger. And if that window approach that maximum value, that delta W is that smaller. This is smaller. This is the reason. And based on this idea, we can say that it proposes TCP cubic. That is, we can, based on that figure, we easy to find it can get the hair throughput because the area under this curve is larger. How to implement, because previously we just +1+1, we linear increase that window. And how to implement this curve? There is a solution. First one, we need have that there is the value k K is point in the time if the window size reach the W max. So each time, okay, this is the K. Okay, K also will update for the different interval. Okay, different stage K. Okay, so for this case, okay, based on this value, we know. So how to increase the W? Okay, increase W as a function of the Q, of the distance between the current time. Current time, like, okay, if we check that like this, like the T. Current time, the distance between current time and the K. So idea is that we use the K minus T, get the power to 3. We consider this value is the increased W. Here's the increased value. Based on this one is feature, we can say if K here, okay, there may be times that eta. Okay, this is a constant value. And so for the K, if T approach K, okay, like T approach this K, so this becomes smaller. So delta W is smaller, okay, smaller. And if K that further away from the K, that is larger distance, and then we consider this is larger. Okay, this is larger. So this solution. So larger increase if that further away from K, and a smaller increase when that the window approach this, okay, the time approach the K. So use this idea, we can implement this, okay, TCP qubit, okay, protocol. Currently, the TCP qubit is used for the Linux, okay, system. And also most of the TCP for the popular TCP for the some web servers, okay, considered, because this is get the better, okay, hair throughput. Okay, so this is first solutions. Okay, we just consider and based on timeout value, or based on the ACK, we determine increase that window or decrease that, get 3 dB ACK. This is based on packet loss, okay, to make decisions. So second one, can we use another solutions? Okay, can we use the throughput or delay to make that decision? The idea is that, okay, so there are some bottleneck link. Okay, we know classical or cubic increase that rate until there are packet loss. So this solution, these two methods, the solutions on top of the packet loss. Can we design some solution on top of like throughput or delay? Okay, so here is this motivation. So for this router, if that busy, okay, it's for the bottleneck link. And for this case is that some packet queue that is almost never empty, but also sometimes is overflow, there are packet loss. And for this case, okay, we need to understand that contraction. Okay, focus on that for if source choose one path from source to the sender choose one path from the source to the destination, and there this node is contrast link. And because we know the throughput depends on that limited or the minimal link capacity. So if we focus on that one link, the contrast link. So for this case, there are two inset. The first one is increasing TCP rate if this is contraction link in here, in the middle part. If we increase sending rate, it will not increase that end-to-end throughput if that there is contraction link. Okay, so reason is that this link current, this value, okay, current that is the smallest, for example. So this current, this value determine, okay, if these are a smallest, minimal. So even though we can increase the other link, okay, the data. So throughput just determine this bottleneck link. This is the motivation. Okay, second part is that if we continue to increase the TCP sending rate, it will increase that matter RTT, because if you check that the queue delay, right? Okay, if that approach that throughput, and finally that delay, current that delay, and this is the traffic. So delay also will increase, become larger. Okay, it will not increase that throughput, but increase the delay. So this is the issue. Can we design one solution, okay, based on that delay? Okay, we check out, for one case, this is unconjected delay, right? That is small. And for the conjection part, we need to compare these two because this one, that delay is larger for the conjection link. So that means current, we need to decrease the rate. Okay, this is motivation. So that means we can keep end-to-end pipe just full, but not fuller, not congest. So use this two motivation, we propose the delay-based TCP contact control. Okay, so that idea is we want to make that the sender and receiver just full enough, but not fuller, not congest. So we make that the bottleneck is busy for transmission, but avoid, okay, the high delay and buffering. How to address that? That means we need to measure that the round trip time, this case. Sender need to measure that. Okay. And previous idea is that we just consider, okay, get ACK. Okay, if you recall the TCP, okay, classical and also the cubic. Okay. And for these two cases that if get 3 duplicate ACK and all timeout value, we cut that. Okay, then not estimate round trip time, not just get ACK. Okay, no matter, okay, that round trip time is large or equal for the first two. So for this case, for delay based, we need to measure the RTT. We need to know what's the value. Okay, if this value, we want first to get the minimum of this value. If this minimum value, that means for this path, this current for this round trip time or round trip this path, this case, there are no conjunction link, okay, bottleneck link if this smallest. So we use this as our benchmark. We consider this is the gold best network condition. And then for the real measured RTT, we need to compare that. Okay, if that approach or near that, okay, smallest RTT unconjected condition, we need to consider, okay, this time the network is very good, we can try to linear increase that window. If that is, okay, further away from that, the RTT minimal. So for this case, we need to consider, okay, this case, the conjection, we need to decrease that. Okay, so this we call that idea is delay-based TCP contact control. Okay, let's check that. So first one is that we need to get the minimal observed RTT. So this is corresponding to the uncongested path. Okay, and based on this value, okay, if we know the window size, it's easy to calculate that uncongested throughput. Okay, so use this value over the RTT, window over time. Okay, so that means this is the maximal value or largest value for here. Okay, another thing is we need to check out the measured RTT. This is real time. We use our number of bits, our data in this interval over the measured RTT. Okay, and for this case, okay, we get a measured RTT. And then we just compare the measure throughput. We just compare the measure throughput and uncongested throughput. Okay, these two things. If they're near, that means currently there's no conjection because that, like this is smallest. We need to linear increase that. If the further away from that this value, we need to decrease that. Okay, so solution is that if measure throughput is very close to uncongested throughput, so that is similar with uncongested. So the path is not congested. Okay, we need to increase that linearly. If that is far below, smaller than this uncongested throughput, we need to linearly decrease this window. Okay, so this is, we can compare with the classical or cubic TCP contact control. This solution, we need to measure the round trip time. And based on round trip time, we can, based on our sending rate, we can get that throughput, measure throughput. We compare, use this one to address that conjection. Okay, what's the advantage for the delay-based? Okay, from here. So it can avoid that the high delay and buffering. Okay, so that is the advantage or improvement compared with previous one. Previous we just based on feedback. For example, if packet lost, then we cut window size. This is very, I think this is very slow reaction for the network connection. And here is that is fast reaction. So because based on estimate round trip time, we can immediately make this decision. We need to decrease or we need to increase that. So because of this good feature, and we can say current, especially Google, develop that the BBR. This is one type of the delay-based TCP conjunction. Okay, so use this solution for the internal backbone network. Okay, for this case. Okay, currently finish that the basic, the end-to-end contract control. So end-to-end contract control, the idea is that we observed like first feature, timeout value, the packet loss. Okay, packet loss. Packet loss, there are two reasons, and 3 duplicate ACK, and the next one is timeout value. Okay, there are two protocol and basic protocol. Definitely there are more. Okay, if you check out the TCP contract control survey, there are more than 200 papers to discuss the different version of TCP contract control. But here we just discussed some famous important, like one is for internet, another one for Linux. Okay, for the TCP, that the classical TCP contract control, and also for the TCP cubic, right? Cubic one. And this is first one based on a packet loss. Okay, second one, we can observe that round trip time. Based on round trip time, we can measure that throughput. Okay, throughput. Based on throughput, we can compare that. Okay, delay based. Okay, we can use like packet loss, delay, throughput to determine that which the contract control. And current solution is we can combine all three factors together. Okay, to design merged TCP contract control solutions. Okay, to get a better performance. Okay, compared with others. This is we can all this one we can say the common feature for the first step, that is end to end, right? This is sender, this is network, and this is receiver. From sender to receiver, this is network. We just sender want to increase the window, this window, or decrease this window, just based on the feedback, these three performance, So there are no any, the middle nodes like router to help or give some feedback, let the sender to increase or decrease that, just based on this performance. So this is the first type of contract control, end-to-end contract control. So second, let's focus on second one. Second one focus on explicit contract notification, contraction control. And for this case, that means definitely the middle node, like the router, can give some feedback information. So previously we discussed that if we choose one path, if this router is congested, we call that is bottleneck link. If for this is bottleneck link, we can use like the delay based to improve the reaction for that congested link. So another solution is that if this router is congested, or can this router notify this information to the sender and receiver? Then if sender and receiver knows this case, then just update to decrease the window. So based on this motivation idea, we consider there is the explicit contract notification protocol, and a router here can help to implement that. So if next chapter, we will discuss network layer, and we need to discuss there are two bits in the IP header, especially in the TOS this field, and these two bits. These two bits can indicate congestion level. If we set 1.1, that means current there is conjunction in one router, in this router. So, and this policy also definitely can determine, be determined by the network operator. Okay, so previously in the transport layer, we can, there are TCP, and for the IP datagram, if that arrival in the network, the datagram, if arrival in this router, if router is congested, so the more pack in the buffer and very slow output rate, and then they need to update that these 2 bits from the 10 become the 11. Okay, and if the destination receiver get that from network and find there is the ECN equal 11, then that will update that flag value in the transfer layer to update the ECE. Okay, to update this one. Okay, ECE in that this value in the TCP header if you check that flag value, and if give feedback for the ACK segment with that ECE equal 1, then sender know there is conjunction in this path. Definitely there are one, maybe multiple routers that are congested. So that will decrease the window. Okay, so based on this idea, we can say this protocol, ECN, involves 2 layers, transport layer and network layer. This is cross-layer design. Network layer also give feedback, and the transport layer also based on that feedback make decision. Compare with the first solution, end-to-end, just estimate round trip time or based on the packet loss, decrease that. And this one is that is given exactly, and also the feedback let the sender know what happened for that router, especially the congestion level. If that congest, so that it decrease that window. We can see that is, we call this is explicit congestion notification protocol. Especially if you check out current architecture, especially I mentioned that for the data center. So Google's or Microsoft data center. Data center network. For data center, there are a lot of that servers. If there is the there is the switch. And this switch connect several servers. Rank stack servers. And then this connect another switch. Another servers. So there are many of this one. And for the data center, there are 2 features. The very small delay here data set. And for that case, we want to reach that sensitive delay, small delay, and we cannot use the slow reaction like previous timeout value or like just estimate RTT. So for that case, we can, for the data center, they want to design that protocol called the DC TCP. So for this case, that use the ECN, borrow the ECN solutions. That use the window of, for example, K bits to indicate the congestion level. Here is just, we can say that I use the 2 bits for here. But for the data center, I need to consider what's congestion level. This is higher level or the lower level, so that I use the bit sequence. And how many bits that is set, that is determines the current congestion level. Currently finish the 2 type of congestion control. Then let's check the other features. The first one is that the fairness goal. For the computer network, we care about that the fairness issues. So if focus on if there are key TCP connections or sections, and share that for the R bandwidth for the link. So each one should have the average rate of R over K. This is we want to reach the fairness goal. Can we reach this goal? So for the TCP protocol, especially for the AMD. Let's check this figure. From this figure, we assume that just the 2 connections share that like this. There are 2 connections share this link, the R. So each one just consider the R over 2, right? And So R2, that is the best case. Okay, so we consider this is the fair protocol or not for the TCP. First one is that, okay, for the connection 1, we consider this throughput rate is R1. This connection 2, this throughput is R2. And this line to show, okay, that is R1 plus, if node here, that means R1 plus R2 equal R. And if one node in this point, for example, here, so that means R1 equal R2. Okay. Okay, this is 45 degrees. An equal balance shell. Okay, so let's check out if any node in this area, okay, for example, in the beginning is here, definitely R1 plus R2 is. If R1 plus R2 smaller than the bandwidth, so that means for this thing also there are additional bandwidth to transmit more data. Okay, for this case, okay, connection 1 and connection 2 can linearly increase that window sending rate. So if that linear increase, okay, linear increase. If that is larger than if R1 plus R2, okay, larger than the R. So for this case, we can say there's contraction. Okay, there are packet loss because the current link cannot support more data, and we need to both sides need to cut the window size in half. Okay, that's this one. This one in beginning here, cut window size in this one here, cut window size. So that become this. Okay, into this point. And then if into this point, also that into here, R1 plus R2 smaller or equal R. So that also linear increase. Okay, if larger than this line, also cut window size in half. Okay, linear increase, cut window size in half. So finally, that way, if that into this line, okay, it will not move out from this line. So for example, linear increase, cut window size in half, linear increase. This is called the equal, okay, bandwidth shared line. Okay, so if that into this one, that means this is the stable stage. Okay, so R1 equal R1 equal R2. So that means TCP support the fire connection for these two two sections. Okay, let's check also. Okay, definitely TCP is fire. Special focus on the connections sessions rather than apps. Later we discuss that. So yes, but also there are some assumptions for same RTT and also fixed number of sections only in the conjunct avoidance level, not in the slow start. Okay, slow start, this is not a linear increase. Okay, so then we consider, so the fairness, okay, regarding the network app. Okay, so like first one, UDP. Okay, some network multimedia app do not use like TCP. Okay, so for this case, if we use UDP to transmit that, we can avoid congestion control. Okay, there are no congestion control. So that just transmit, okay, as soon as possible. Okay, no increase window or decrease window. If we have data, we can transmit. Okay, and if let's check out some parallel TCP connection. So if one app can open multiple parallel TCP connections, okay, like your first, this midterm exam, I discussed that, right? For the HTTP connection, we choose non-persistent and persist. We can use the multiple TCP connection. And for this case, okay, there is example, if the web browser, and for this one, use the non-existing connections, well, shares are. So if new app asks one TCP connection, so finally, okay, this new app just used R over 10. Okay, so just share, okay, 1 over 10, that's the, okay, that rate, the transmission rate. And if another new app join here and apply the 11 connections, okay, for this case, okay, even this new app, this time we can say that can share near, we can 11 over, okay, we can say 21, okay, near the R over 2. So this new app share R over 2's bandwidth, but this new app just share R over 10. So this is unfair for the different apps, but the TCP support the fair connections section. So that's for each of these TCP connections, this is fair. But for app, okay, we can do the more connections. Okay, last one in this topic, we focus on, okay, the features for the transport layer functionality. So we know for TCP and UDP, okay, were used for the more than 40 years. Okay, that if you check history of internet, okay, and for this one also very great. Okay, some app use UDP, some app use TCP. Okay, but currently there are different flavors of TCP development. Okay, for example, for the different scenario, specific scenario. So first one is if we consider some non-fed PAPs to transfer the larger data transfer. So for this case, some challenge like, so the many packet in flight, okay, so for this, especially for this larger data. And if there are packet loss, it will close this pipeline. Okay, this is issue for larger data. And the second one for the wireless network. For wireless network, we need to check wireless features. Okay, so the packet loss because of just noisy the wireless link and users' mobility. Okay, and for these two features, we can say this is not a congestion for the internet. This is just not a stable link, wireless link. So TCP also treat this as congestion noise. Okay, third one, that is the long delay link. So for example, someone, okay, for the satellite network, right? For this case, there are very, okay, long, okay, latency, okay, very long round trip time for this case. Okay, for the long delay link, for the satellite, also we need to consider how to set that timeout intervals. Okay, another case for the data center network. For the data center network, I mentioned there are two features. Okay, small delay, higher, okay, that throughput. This is the latency sensitive features for the data center network. So for this case, we also need to update the contact control protocols. Okay, and the last one is some, okay, like the cloud computing, some background traffic flows. For this one, has very low priorities. Okay, so how to use that, update the contact control levels. Okay, for the different TCP flows. Okay, consider some priority features into that. And we know if we use the TCP, okay, and we need to consider different version of the TCP. Someone use delay, someone consider the packet loss, and someone consider the network assistant. Someone also need to update some features, also treat of the like the wire link or other thing. So there are not the common, okay, that features for all the different scenario. So, and also this is the internet architecture. This is lower layer, right? Rather than the user space. So current one treat, okay, this we move the transport layer functions to the application layer. Okay, so can we use UDP? UDP is simple. Know these issues. For different cases, for the wireless, for the long term, or like this case, we can implement that idea, the contact control or reliable data transfer in the application layer. Okay, we can move that on top of UDP. So based on this idea, okay, we can say the Google post the QUSC, okay, the protocol to support HTTP3. So what is QUSC? I think I discussed this in the last chapter. Okay, this is quick UDP internet connection. Okay, so we use the UDP as the transport layer architecture, and we can move the functionality in the application layer. So based on this one, we can increase the performance of HTTP, and this protocol currently is deployed by the Google's servers or apps, okay, like YouTube app or Chrome. And let's compare with that two different architecture. First one, HTTP version 2, and this is on top of TCP. Okay, and then we use HTTP 2 versions, and if we consider security, use TLS. And then another one is use the UDP, and for this here, we just to combine the HTTP 2 some mechanism. okay, protocol and just slimmed that HTTP2 and combined the QUSC. So this is creating a new protocol called HTTP3. Okay, together to get this. Okay, so there are some features why we use that QUSC. And one is that if we currently learn, we near finish this chapter, we discussed multiple features in the TCP, okay, like the error detection based on checksum, contact control, right, flow control, right, three handshaking, right, and reliable data transfer. If we are familiar with this one, we discuss one by one for that in detail for the protocol. Then if you want to use QUSC, we can implement that basic functions into the application layer. Okay, so from the QUSC specification, you can check that. And also we can do the connection establishment for the QUSC. Okay, so for this case, all that reliability, contact control, authentication, encryption, state, establishment just needs a single RTTs. This is the features. So we can use the single QUSC, we can support multiple stream, okay, that transmission. And also we can, okay, separate the security and reliable transfer and use the common contract controls. Okay, so first one, compare with that the traditional that TCP plus that security, like TCP plus the TLS. Okay, and that is the two-stage, three-way handshaking. Okay, so set up that connections. And the second one, we also need to use like another section for the security part. Okay, TLS handshaking for the security. Okay, for this case, okay, that need to use the two serial and handshaking to set up the TCP connection and security, add security features. And second one is that if we use the QUSC, and if we just have the one handshaking, we just one handshaking, including all the things, reliable data transfer, contract control, authentication, okay, or cryptography state. So we can reduce, based on the QUSC, we can reduce round trip time. Okay, let's check out, okay, for the QUSC, how to address that non-header LAN blocking issues. Okay, let's see these two figures. The first one, that's just traditional HTTP 1.1. And from here is we can see in the transfer layer that implement reliable data transfer, contract control. And the application layer, there is library for the TLS. And there are some HTTP GET, okay, that is the protocols. And this is receiver. And for the QUSC, this protocol, and we transfer layer, we just use simple UDP. And application layer, we can add the contract control or reliable data transfer and security together in here. Okay, so let's check out this first case. And if we transmit request object, okay, if second one, there is error in the transfer layer. And there are errors, so I need to retransmit this. Then, okay, transmit third packet. So there is a header LAN blocking. Okay, third one need to wait for the second one for the finish the transmission. Now here is there an error. It will not influence the third one for transmit from okay source to the destination. Okay, then transmit the new segment. Okay, this is the good feature for QUSC. If you're interested in this QUSC, you can check out Google that for the more detailed check the specification for the QUSC. Okay, here we finish this chapter. Let's quickly summary. Okay, this chapter 3. Chapter 3 also very important because this chapter support application layer. There are two protocol, UDP and TCP, right? We discussed that feature. The transfer layer support the application layer. It provides end-to-end virtual connections between two processes with the host, right? And this layer also on top of network layer, okay? And so that means this first packet need to arrive at the correct destination. Then the transmitter need to determine this is the correct packet or this is corrupt packet for the reliable data transfer. Okay, And in this chapter, also we discuss UDP. This is very simple, right? It's a small header. And we discuss multiplexing, demultiplexing. Okay, packet arrival receiver. We need to use the, for the UDP, use destination port number. TCP use 42 source and destination port number and IP address to direct a segment to the appropriate socket. Okay, we discuss reliable data transfer from RDT 1.0 to the 3.0. Okay, so you need to definitely review that and to prepare for the midterm exam. And also we discussed the pipelining protocol, go back and select repeat. After this, we discussed okay, what's different between the flow control and the contract control. Flow control regarding, okay, the receiver buffer, not overwhelmed receiver buffer. So it's easy, use the window to give feedback. Okay, contract control regarding the network, okay, buffer. So for this case, there are two types of contract control. One is end-to-end, another one is network assistant. End-to-end, we based on observed, okay, that feature, like the packet loss, like the round trip time, or like the throughput, we can increase or decrease that window. Especially we discussed the TCP classical contract control, okay, like AMD, and also we discussed the cubic, okay, to improve the throughput. We also discussed the delay-based, right? And for the, okay, second part is for the network assistant page, we discussed, okay, we use that network update, okay, ECN value from 10 to 11, then, okay, receiver, okay, give feedback, okay, in the transmit areas from the ECE from 0 to update to 1. So then sender update decrease that window. Okay, and then after, beyond this, we discuss QUIC. Okay, on top of UDP, we can implement all that feature in the application layer. Okay, so next chapter, okay, we also have the 15 minutes. Let's, okay, just the start or give the basic idea for the next chapter. Okay, this chapter first, okay, we, for network layer, current for the new textbook, that is separate into two plans, two chapters. So first chapter, chapter 4, we focus on the data plan. Okay, so regarding the IP, how to get IP address, right? And how to do the forwarding. And the second one is chapter 5. Okay, we discussed about the control plan. Okay, so how to do the routing. Okay, how to implement the routing algorithm. Okay, so you don't need a camera. Okay, this is our university policies. Okay, so you just to finish by yourself. Okay, upload. Okay, on time. Okay, you don't need a camera. Okay, let's continue. So we know chapter 4 focus on data plan, chapter 5 for the, okay, control plan. And this is good for this chapter. First, when we focus on the data plan, okay, we need to understand that principle of behind network layer. Okay, focus on data plan. We will learn network layer service model. We discuss that provide logical end-to-end connection between two hosts. Okay, we need to find a destination device. This is our destination goal for the network layer. And there are two functions. And in the chapter 1, also I discussed network layer. Network code, there are two functions. One is forwarding, okay, for the per router. We forward that from input to output. Now in routing, we need to find least cost path from source to a destination. Okay, we used the two chapters to discuss these two features. But also there are some protocols, how to get IP, how to transfer, okay, from one IP to another IP, right? Or what's different between like the IPv4, IPv6? How to implement a general case, okay, that forwarding, okay, for this one, and what's inside of that router, okay. So there are a lot of things in that the data plan, like we discussed IP address, network address translation, middle box in this chapter. Okay, network layer, we know that current separate into the data plan and the control plan, and also for roadmap, we first discussed this. I think this is very simple and clear. And then we discussed what's inside the router. We discussed router input and switching output port. We consider the router's buffer management. We know that packet arrived at router, how to address that, how to address the longer delay, right? How to schedule that router over the link to another router. Okay, another case is that for the internet protocol, Okay, we discuss what's the IP format. Previously, we discussed TCP format or UDP format. Here, we discuss IP format. So the datagram format. And also, what's the IP address? What's the subnet? Okay, and how to separate subnet? What's the network address translation? Okay, from one address to another address. And what's the difference between the IPv4 and IPv6? Okay, so another thing is I quickly introduce the basic thing for the SDN, because for our final there are no concept regarding SDN. Okay, just give it additional information. But before this is very important. And also we discuss current, special Google, Facebook, that for the larger network we want to do the SDN, software-defined networking, to use the match and action to forward that packet to deliver that. Okay, first thing, let's also consider, this is common things. Okay, we check that the network layer service and protocol. We know network layer connect to transport layer and link layer, okay, in the middle. Okay, if transport layer get the segment and then deliver that segment to the network layer. Okay, network layer also need to add a header, okay, to create a datagram. Okay, and then if network ready, we need to deliver to the link layer to add a header to create the frame, right? And for network protocol, also in every internet device like host. Okay, we can say the host switch. Okay, especially we can say for the routers. And another way is router just, okay, what's the function for the router? They need to examine the header, okay, in the network layer, in the datagram, and check the IP, special destination IP. Based on the IP, we can move that datagram from the router's input to router, which output depends on the destination's IP address. So let's compare again for the, okay, for that, we review again for the network layer functions, two key functions, forwarding and routing. Forwarding idea is move the packet from router input link to router's output link, okay, from this per router. Routing is to determine one path, one route taken by a packet from source to the destination. So maybe we use the least cost as our object function, okay, for the design of routing algorithm. Okay, so like this trip as example, if we consider the forwarding like process of getting through the single interchange, and for the routing here, they need to consider the process of planning trip from the source to the destination. Okay, so from network layer, we know we separate network layer into two chapters, two plans, data plan and control plan. So first one is data plan. I think in the chapter 1, we discussed this. Here, we just review that. For the data plan, that means focus on this per router, okay, function. And that determine, regarding the forwarding, determine how the datagram, okay, arriving router input is forward to the router output. For this arriving packet, we need to forward from router input to router output. And what's the control plan? Control plan from the global, from the network valid logic to see that. So that need to determine how the datagram is forward from source to the destination, okay, over that, okay, this path of the routers. And for the control plan, also there are two methods. One is traditional routing, okay, we can implement in current router, and that is the decentralized solution. Second one is the SDN based, okay, the software-defined networking based. In the special next chapter, I will introduce that. Okay, first one is for the per router control plan. We can see each router there is the local forwarding table, their header, their output link. For each router, we need to consider to implement that routing algorithm. For example, we can use the Dijkstra algorithm. Okay, find the least cost the path from this source to another destination. Okay, so upper layer this is routing. Lower layer for the router for here, if get that data, we forward from input to output. This is forwarding. This is regarding data plan. Okay, for the SDN level, so there is the remote controller. Okay, so that will install the forwarding table for each router. So this is control all the router. Previously, this is decentralized. Each router just run a algorithm. its algorithm to forward that packet from one router to another router. Okay, based on that features, okay, we can say for SDN-based control plane, also there is control plane or data plane, and there is remote controller to give that to interact with that these routers, give that forwarding table and detect some the traffic or other things. Okay. And what's the network service model? Okay, so and previously for the transport layer, we also discussed that. And here for network layer, also what's the network service model? Okay, to transmit for the channel to transmit the datagram from sender to receiver. So some example service like for the quality of experiments, like for the individual datagram, like can we guarantee like delivery, like reliable data transfer? Second one, can we deliver that packet with the small latency? Can we guarantee that less delay, a small delay? Okay, someone service like for the one flow example, can we deliver that datagram in order? Okay, can we consider guaranteeing the minimum of the bandwidth for the flow? Okay, can we restrict on the change in inter-packet space? This is all that feature we call that is QoS, quality of service. Can we provide that service? Okay, so the answer is no. For the internet, okay, the basic, the network layer service that is used best effort. Okay, so the best effort that I mentioned that in earlier chapter. So this doesn't guarantee any features, just transmit that. Okay, it doesn't guarantee the minimal bandwidth, doesn't guarantee the packet loss, orders, timing. Packet loss order we address in upper layer, transport layer. If there are packet loss, we can retransmit that. If all the order in the transport layer, we can also retransmit that. Okay, timing and bandwidth. Okay, no protocol, current internet protocol can guarantee these two things. This is the basic feature for that link. So what's the internet best effort service model? Okay, so that means there are no guarantees on successful datagram delivery to the destination. So that means in the transport layer, we didn't assume that the lower layer is reliable. So we will consider, okay, network layer is unreliable. So we can say because network layer use the best effort service model, no guarantee on successful data delivery. For this case, we can do that on the transfer layer. And no guarantee on the timing or the order delivered for the datagram. Okay, so this also we consider for the transfer layer. And no guarantee for the bandwidth available for the end-to-end throughput. Definitely, there are other network architecture. Okay, so like the ATM. Okay, and this is asynchronous transfer mode. Okay, for this case, there are two service model: constant bit rate or available bit rate. And for this one, we can guarantee the constant rate. Yes, yes, yes. Okay, this is guaranteed minimal, and for the order, and for the specific to internet service, and this is the integrated service guarantee. So that can guarantee all the things for this document. And another one is differentials the service and for check all this document. And this is okay, just use the soft that service. So possible, maybe guaranteeing this, maybe not. Okay, this is hard. Definitely need to guarantee this one. But our traditional internet just use the best effort. No guarantee all that four things. We call these four features that is the quality of service. Okay, so in order to implement the quality of service, the model in the network layer, so that need to check all the like integrated that guarantees models. Okay, so we want to reach the QoS. Okay, we know with all this one, current internet is good, it's great. Okay, so there are some voice regarding reflections regarding that best effort service. Okay, because that's simple, right? So alone internet be widely deployed and adopt now. Okay, and also that provide some sufficient the bandwidth alone. Okay, this one alone that real-time applications to be good enough for most of the time. Okay, all other things, okay, contract control or other things, service care for the best effort, like reliable data transfer, contract control, flow controls. Okay. Okay, so the current also there is hard to argue with success or best effort that service model, okay, for the internet. So some papers also discuss like the other options, okay, to guarantee all this QoS based. Okay, let's finish here. Currently, I just give the basic, big picture for the network layer. And next week, first class, also let's continue to discuss what's inside our router. Okay, so you need to prepare your midterm exam to try to finish your homework. Okay, thank you. Okay, you are not needs the camera.